Hello everyone. My name is Siddarth Asokan. I'll be presenting on the optimality of generative adversarial networks, or GANs, viewed from a variational perspective, which is my PhD dissertation topic. I'd like to thank BMVC for giving me this opportunity to present at the Doctoral Consortium here today. While I've recently joined as a research software dev at the Microsoft Research Labs in India, I'll be presenting my PhD research work carried out under the guidance of Professor Chandrasekhar Silamantula at the Indian Institute of Science, Bangalore, India. Before we dive into the main topic, let's start with a brief introduction to generative modeling and in particular GANs. A generative model in the most fundamental sense is typically a neural network based approximation of a given target data distribution. The modeling is done with hopes to either estimate the likelihood of test samples or to generate novel samples never seen before. While my talk today focuses primarily on generative adversarial networks or GANs, we'll also come across and develop strong connections between GANs and autoencoding, flow-based, and score-based generative models. Alright, to set the stage, GANs model a min-max game to learn the target data distribution, which in this case are metphases images viewed as coming from an underlying distribution P suffix d. The generator then learns to transform parametric noise, typically Gaussian distributed, into samples following an output distribution P suffix g. The discriminator is tasked with differentiating between the real and generated samples and relay this information back to the generator through appropriately defined loss functions. The objective is to learn the optimal generator. Throughout this talk, we'll be looking to pick apart the various components of the GAN and understand their optimality, deriving optimality conditions based on functional calculus and differential equation theory. In particular, we'll be looking at the GAN discriminator and generator optimality from an analytical standpoint in parts 1 and 3, and in part 2, we'll explore a more implementable and scalable approach to picking optimal generator inputs, leveraging insights from part 1. First, let's consider the GAN discriminator. To start things off, let's focus a bit on the losses used to train various GANs. Broadly, there are two kinds. The first and the classical formulation is that of divergence minimization. For example, the standard GAN involves a cross-entropy loss, and the generator can be viewed as minimizing the Jensen-Shannon divergence between the data distribution PD and the generator distribution PG. Similarly, the LS GAN considers a least squares loss corresponding to the Pearson chi-square divergence. On the other hand, we have integral probability metric GANs such as Wasserstein, Sobolev, and Fisher GAN, where the choice of IPM results in a corresponding constraint class for the discriminator. The most popular among these variants is WGAN, which considers Lipschitz 1 discriminators. In practice, however, the Lipschitz constraint is challenging to implement, and variants such as WGAN GP, WGAN LP, etc. enforce a gradient penalty to approximate the constraint. This table encapsulates some of the most popular gradient regularized WGAN variants. A key ingredient in our analysis is variational calculus. The optimization of integral costs, such as script L shown here, involve optimality conditions on the integrand script F. These conditions on the first variation, akin to first order conditions on the derivative in variable optimization, are known popularly as the Euler-Lagrange condition. Of course, one could also dive into higher order conditions to check for the kind of extremum, etc. These concepts will be core to deriving the optimality in GANs. As an example, consider the standard GAN loss. The expectations rewritten in their integral form fit within the Euler-Lagrange analysis framework, the integrals being defined over the convex hull of the supports of PD and PG. Applying the EL condition yields the optimal S-GAN discriminator, which is consistent with the result derived with pointwise optimization in the baseline work. The EL approach also yields the derived optimality condition that PG star is PD, the data distribution, when considering regularizers that enforce PG to be a valid distribution. While I merely summarize the results here, similar derivations for all major FGAN variants can be found in our JMLR paper. These results showcase the validity of the proposed approach. We also derive general solutions to non-saturating GAN losses and their training stability, and LS GANs with any choice of class labels, giving rise to a few custom GAN variants. As a detour, let's look at one such custom GAN, which is the Rumi GAN formulation built atop a contrastive learning principle of learning to ignore. In particular, we consider a GAN discriminator that is shown both positive and negative class samples, while we model the generator to learn only the positive class. For the LSGAN family, we not only reformulated the original loss to incorporate a weighted mixture of the positives and negatives, but were also able to show via the EL analysis that there are guarantees that the generator learns only the positive class, while the discriminator is shown both the positive and negative class samples. In this NeurIPS 2020 paper on RumiGANs, we were able to demonstrate learning with simulated imbalances on various datasets and showcased competitive performance, at least at the time, on up to 192-dimensional class imbalance cell A. Coming back around, a more interesting use case for this analysis is the WGAN loss with a gradient norm penalty enforced uniformly over the support script X. This loss, when analyzed within the EL framework, yields a Poisson partial differential equation that governs the optimal discriminator D star. In this work, we explored a Fourier-series approach to solving the PDE. Considering Fourier-series expansions of the data distribution PD, generator distribution PG, and D star, we showed that the Fourier coefficients of PD and PG can be computed by evaluating a sample estimate of the characteristic function at the desired harmonic omega m. This gives us a closed form expression for the coefficients of the discriminator. While detailed truncation and approximation error analysis are present in the paper, the resulting Fourier-based discriminator is implementable via a two-layer network with pre-computed weights and sinusoidal activations. As a use case, we employed the closed-form discriminator in latent space matching tasks using Wasserstein autoencoder, giving rise to the wafer framework. Wafer demonstrates superior performance with improved convergence without the need for training classical GAN discriminators. These are also corroborated in terms of FID, reconstruction error, and image sharpness metrics on various standard datasets. While I won't go into the details in the interest of time, we also extended the analysis to higher order gradient penalties in WGANs. In general, we were able to show that the optimal discriminator in these GANs solves an iterated Laplacian PDE, resulting in polyharmonic kernel-based radial basis function discriminators. Hence the name polygans. And an in-depth analysis linking the polygon discriminator to higher order Sobolev spaces and mesh-free kernel interpolation can be found in our Interpolate NeurIPS 2022 workshop paper or the extended version currently under review and available on archive. Let's switch gears now to the GAN generator input. We hypothesize that while the parametric input to GANs might be too unstructured to efficiently model data manifolds, existing image-to-image translation GANs were too restrictive in their choice of input. We therefore formulated spider GANs, where the idea is to pick a friendly neighborhood input dataset to the generator, given a choice of target. To identify these friendly neighbors, we repurpose the kernel-based optimal discriminator to define the signed inception distance or SID, a measure of similarity between two datasets computed by evaluating the polygon discriminator over inception embeddings of samples drawn from the source and target datasets shown in red and blue, while uniformly drawn samples centered about the target are references in green. SID takes small positive values when a source is more diverse but close to the target manifold, but negative if the source has less sample diversity compared to the target. Training the SpiderGAN generator with friendly neighborhood inputs, such as celeb A as the input for MNIST or ImageNet as the input for celeb A, results in significantly faster training. These models are also able to map structures that align between the domains or perform class-based clustering, even though no such constraints were ever enforced. For example, the model learns to map the trouser class in fashion MNIST to the digit class 1 due to underlying structural similarity. However, the clustering of the airplane class to similar ukiyo-e faces is more implicit, with no visual similarity between the two datasets apparent to us. We also explored utilizing this framework to come up with a novel variant of transfer learning. We developed cascading versions of SpiderGAN where the output of a pre-trained existing GAN generator could be leveraged to accelerate training a subsequent stage. Here, instead of transferring weights, which one could still do, we transfer the input distribution. Cascaded spider style GANs on small datasets such as FFHQ, AFHQ cats, met faces, ukiyo-e faces, etc. results in state-of-the-art performance in a fifth of the training time. Cascading allows us to perform interpolations on both the first and second stage inputs. With a single GAN capable of generating both diverse but coarse transitions in stage 1 interpolation, but finer transitions in stage 2 interpolations, as demonstrated by this animation. Remember that both rows of the output interpolations are from the same generator here. Additional experiments on comparisons to baseline style GAN variants can be found in our paper. Lastly, we move on to the GAN generator. Consider a brief introduction to score-based models. These techniques model the corruption of images with noise as a forward process governed by a stochastic differential equation or SDE. The generative process reverses this SDE and typically involves the gradient of the log of the density, also known as the Stein score. A neural network is typically trained to model this score, which can subsequently be used for generative modeling using Langevin sampling. With the standard GAN example yet again, we consider the alternating optimization of the generator and discriminator. First, at time t, given the generator at the previous iteration, we have the distribution pt-1 associated with its output. pt-1 is then used to derive the discriminator dt star. Subsequently, dt star is used to update the generator, thereby giving us gt and its push-forward distribution pt. Within this setting, we show that the optimal generator GT is the one that achieves score matching between the score of the data, grad log PD, and that of the generator's current push-forward distribution, grad log PT-1. In fact, these results hold for all FGAN variants. A similar analysis on the gradient regularized WGAN generator results in flow matching over the gradient of the kernel, which we showed was equivalent to score matching with a smoothed version of the score, the smoothing kernel being the kernel associated with the PD of the optimal discriminator. Intuitively, FGAN generator training hopes to achieve score matching, which can be unstable, especially as seen here when the generator and data distributions are far apart and the score is weak. However, in addition to the attractive forces towards the target induced by the score, the kernel gradient from WGAN variants also provides a repulsive force away from the generator distribution at any given time instant, accelerating and stabilizing training. One could also view this as achieving the same goals as noise-conditioned score matching proposed by Song et al. This helps explain the training stability of WGAN variants while also analytically validating recent trends in network-based discriminator-guided diffusion. For example, comparing score fields against the discriminator gradients learnt in the standard GAN upon convergence, we observe a stark similarity since the GAN discriminator is indeed trained to model the log of the density ratio of PD to PT-1, which in turn results in score matching in the generator. We also use these insights to analytically formulate and justify discriminator guidance in score-based Langevin sampling and also proposed a kernel discriminator-guided Langevin flow. This figure illustrates a 2D example of such a kernel discriminator guided flow of the particles from one distribution to another, while this animation demonstrates the use of kernel discriminator guidance in modeling MNIST compared against noise conditioned score matching. The discriminator guidance convergence is much quicker, although image quality clearly needs more improvement. Nevertheless, the key takeaway is that the models on the left need no training at all and involve a kernel interpolator computed entirely in closed form. To summarize, across this talk, we analyzed GAN optimization from a functional calculus standpoint and derived optimality conditions on the GAN discriminator and generator. A novel distance function built atop the optimal discriminator serves to improve GAN generator training by identifying superior choices of input to the generator. Looking ahead, there is clearly a lot of scope in fleshing out the theory that unifies GANs, diffusion models, and score-based Langevin sampling approaches. One could certainly leverage insights from one field to improve another. These are the publications that came out of this work contributing to my PhD, and these are some of the key references cited across this talk. Thank you all for your attention.